Hello.
Hi,
Hi, how are you?
good. How are you?
I'm good. So I got the material that you sent me. From the PowerPoint, is there any conceptual stuff that uh, you have any questions on?
Yeah, let me pull it up.
Okay.
Um, kind of like towards the bottom more.
Mm-hmm.
Like just like the difference between like the Lewis acids and bases
Mm-hmm.
and like the Bronston Lowry
Mm-hmm.
ones. It's kind of a little bit confusing.
Okay. So, yeah, so there are three definitions of acids. There's the Arrhenius one, which basically just says that an acid will produce like H plus, and a base will produce OH minus. And that comes from water, from dealing with water. The Bronson-Lowry definition is, um, well, for an acid, it's a proton donor, and for a base, it's a proton acceptor. And the Lewis base and acid definition is the base is a lone pair donor, and the acid is a lone pair acceptor. So the Lewis definition doesn't need to have any protons or H plus. Um, so it's a lot more applicable for like later on, like if you do like organic chemistry or something like that. But but yeah, that's basically what a Lewis base and acid is. And I see that they drew ammonia as an example on the last slide. So ammonia basically has that lone pair, the two green like electrons, and
Mm-hmm.
then we have boron trifluoride, I guess, which acts as a Lewis acid. So basically, what's happening is, um, if you could imagine like an arrow going from the lone pair of ammonia to the boron atom, um, it makes like a connection with it, um, and acts as and that's the Lewis base and Lewis acid reaction. Usually, what happens is that it makes like a chemical bond. Um, and then we have some more examples with fluoride ion and H plus ion. So, we have like boron, I guess, tetrafluoride and ammonium ion. So, yeah, so the Lewis definitions just, yeah, they don't require protons and they cover every case, which means that, like, a Lewis the Lewis definition is true for all acids, including Arrhenius acids and Bronson-Lowry acids and bases, but it's not the other way around. Like a Arrhenius acid is not technically like doesn't necessarily have to be like a Lewis acid, but it goes the other way around. Does that kind of make sense?
Yeah, so it's kind of like the overall like
Mm-hmm.
definition of like acids and bases kind of.
Mm-hmm. Here, let me share my screen. Okay, you can see this, right?
Mhm.
Yeah. So like, if I were to draw it like, let's see, um, Arrhenius acids, Bronson-Lowry, and Lewis. I don't know why this pen is giving me a hard time, but um, yeah, basically like um, like an Arrhenius acid can also be a Bronzed-Lowry acid, but a Lewis acid or base will always be both Arrhenius and Bronzed-Lowry.
Mm-hmm.
Okay. All right. Anything? Yeah. What else from the PowerPoint?
I think slide. Let me see it.
Oh, does it make sense how you find pH?
pH.
pH, yeah.
Yeah, I think so. Like it. I don't really know if I get it conceptually, but like
Mm-hmm.
stepwise.
Oh yeah. What about logarithms?
Yeah, like the anti-log and the negative log.
Yeah. So
Yeah.
like a logarithm is basically the inverse of an exponent.
Mm-hmm.
So it's a way for them to talk about like an exponential increase, but make it appear like it's a straight line. Because like for instance, like so like pH. Okay. I was going to write. I don't know what this pen. Let me get another pen. Okay. So. Okay. pH is the log of the H plus concentration. That's a negative in front. And okay, so basically, like, since it's a log, like a 10 times increase corresponds to like a plus 100 times increase is like plus 2. So if I were to like graph it like 1, 2, 10, 100, it would look like kind of like that.
Mm-hmm.
So yeah, but if I graph like the pH though, it would just be like a straight line, like 1, 2, like pH over here, and like H plus. So like, sorry, pH over here, H plus. So it's just a way for, you know what? I have a better notebook where I kind of talk about that, but yeah, just a way for you to. Okay, I mean, all right. Yeah, okay. So it's just a way for you to deal with really, really large numbers in a linear way. So, like, because there's, like, obviously going to be, like, a really large number of, like, H plus ions and things like that. So, um, okay, if for instance, like, in the first slide, it says, what is the pH of a solution that has an H plus concentration of 1 times 10 to the negative 4? So, what do you think? How would you do that?
You would plug in the concentration to the negative log.
Mm-hmm. Yeah. So here, I'll show you a trick. What you can do with this formula is you basically take the exponent and you subtract it by the log of that number that's in front of the exponent, like the number that gets raised to like the exponent power. I think it's called the mantissa. So exponent minus log of the mantissa. So for instance, for this problem over here, the exponent, so the e thing makes sense, right?
Mm.
Okay, so this thing is just going to be negative 4, the exponent, minus log of the mantissa, which is the 1. So what's log of 1?
That's just
Mm-hmm.
10?
So like, alright, so log of something, so like log of x, let's say, is equal to a, like up here. The base of the log is a 10, so you could think of it as 10 to the a power is equal to x.
Oh, is it 0?
Yep. So it'll be neg 4 minus 0, which is just negative 4.
Mm-hmm.
I forgot the negative log part. So it's actually going to be negative exponent minus the log. So this will actually be negative 4, which is just positive 4. So the pH is a 4.
Mm-hmm.
And pOH is just like, because pH plus pOH is equal to the P of water, which is just 14. So if you wanted to find the pOH of this, what would that be?
You would just subtract 14 by 4, and that would be 10.
So the pOH would be 10, right?
Mm-hmm.
Okay. And then they ask, what's the H plus concentration of a solution with the pH of 2.54? So yeah, you would just do it backwards. So like, pH of 2.54. Actually, there's a trick to this also, which is just take whatever the so it's 10 to the power of negative pH to find the H plus concentration. So if it has a pH of 2.54, the H plus concentration is 10 to the power of negative 2.54. Okay?
Yeah.
All right. All right, what's the difference between a strong acid and a weak acid?
A strong acid is basically anything that disassociates or ionizes like 100%, and then everything else under 100% is weak.
Perfect. What's capital K A and KB?
That's the well, the A is the acid, the B is the base, and then that's the
Yep. So anytime you see like the capital K, it's a version of this thing called the law of mass action. Have you heard of that?
I don't think I remember it.
Okay. Yeah. It's something that comes up every time you see a capital K, and it's basically going to be something like the concentration of products over the concentration of reactants. And yeah, so you'll see like basically you'll see like K equilibrium, Ka for like association or like for acids, Kb, you'll see Kw for water, which is the autoionization of water. Tell me about that.
Well, I just know that like water, it can tell you about K like W or like
Mm-hmm. Wait, what's
just
that?
water.
Uh,
Just
what's what's autoionization of water? What does that mean?
um well, I know like water can act like either acid or base.
Mm-hmm.
It can like donate like the H plus or the
Mm-hmm.
OH minus ions.
Yep. So basically, what that is saying that autoionization means that it ionizes like itself. So if I had H2O liquid plus H2O liquid, it can turn into like let's say like this one donates a proton, right, and this one accepts a proton, and so let's say okay, if H2O don't like loses a proton, what does it turn into?
OH minus.
Good. And then if it gains one, what would it turn into?
H3O plus.
Yeah. And by the way, like whenever we talk about H plus, what we're really talking about is H3O plus, because it's like the H plus is just a proton, and a proton you can't have like a proton just randomly, you know, moving around in solution. So yeah, it's really the hydronium ion. So yeah, this is autoionization of water, and like so K whatever W for this would be like OH minus concentration H3O plus concentration. Since we don't include liquids in anything regarding like this law of mass action, it's just going to be this times that, and that's KW. Okay, and oh yeah, I was right. It is the mantissa. Okay, I just saw that in the PowerPoint. And then okay, anything else in the slides?
Yeah, I think find which day it is. It's slide 42.
Okay.
It's just like the salt. It's like reactions with like salt problems.
Okay.
It's just like it's a little confusing because you have to like break up the element.
Mm-hmm. Are you talking about like conjugate base?
Yeah.
Oh, you're saying if you add a salt to something that breaks up into a conjugate base, you'd have like a common ion effect.
Mm-hmm.
So, all right, so let's say you have a weak acid. So, like acids, like once they do their job, it turns into like a conjugate base, and a base would turn into once it does its job would turn into a conjugate acid. So in this slide, or yeah, on this like slide, it says acetic acid turns into its conjugate base, which is C2H3O2 minus, and a salt from that ion is just adding like sodium to it, so it forms an ionic bond with the negatively charged conjugate base. So let's see, if you placed the salt into water to make an aqueous solution, how would the pH change? Okay, so we're just adding it to water, and it dissociates into Na plus and C2H3O2 minus. So you're gonna get a conjugate base basically there. Now, how would the pH change? The conjugate base, it should raise the pH slightly because it's going to act to take protons away from H2O. So the pH should go up, but not by much. And then we have another example with HCl. And then Cl minus is a negligible base. Oh yeah, that's another thing. So like weak acids would produce a stronger conjugate base compared to a strong acid. Because if you think about it, since a weak acid isn't doing its job 100%, its conjugate base is going to have to pick up some of that slack. Whereas if it's a strong acid, it's completely doing its job, like by disassociating, and the conjugate base can't do anything because it can't really act as a base. Like for the HCl, the Cl minus is not strong enough of a conjugate base to take like a hydrogen back to make HCl.
Mm-hmm.
Whereas for the acetic acid one, since it's not completely dissociating, you're going to have still some, C2H3O2, like the acetic acid, you're still going to have some of that left. So the conjugate base is going to be able to deprotonate that some more. And then for these questions where they ask you if you place a salt and how the pH would change, for like adding NaCl, it's not going to really change anything because the chloride ion is a really, really weak conjugate base. So how would the pH change? It basically wouldn't change.
Mm.
Okay. Does that kind of make sense?
Yeah.
Okay. I see. All right. H2SO4, sulfuric acid. Its first conjugate base, amphiprotic or amphoteric, meaning it can act at, yeah. Okay. If Ka is greater than Kb, the anion tends to decrease pH. If Kb is greater than Ka, the anion tends to increase the pH. Does that part make sense?
I remember it did when I heard it the first time, but then I kind of now read it back.
Mm-hmm. Oh yeah, I found like something from my other student that is exactly what we're talking about. So yeah, Ka times Kb is equal to Kw, which is 10 to the negative 14th power. pKa plus pKb is pKw, which is 14. This is auto-ionization of water. And did I talk about anything else about here? Oh, okay. This is for polyprotic acids with titration. And okay. Sorry, what were you saying?
No, I like that kind of help right there, but
oh yeah, here's one on logarithms. This is what I was trying to find initially. Like, why use them, right? So like if this is for like decibels, which is different, but well, I mean not different. Like it's still gonna use logarithms, but so like if this was like the okay, so basically what happens with like when you would use a logarithm is when there's a small, like this narrow range between these two like red vertical lines, and it rises. There's a huge variation. It rises, like it changes so much in that small narrow range. So we use logs to describe numbers that vary by large amounts in a small range. So if we use the logarithm, if we take the log of this, it would just be a straight line. So that's just like conceptually what it's for. And like here's also kind of like a graph for it. Like let's say you have something that's 2 to the x power, like, you know, an exponent. And this is y, the line y is equal to x. The logarithm of this is just a reflection over to the line y is equal to x. So in other words, it's a way to take real life data that's a curve and make it a line so it's easier for us to conceptualize. So, okay, yeah. So this is what I was saying before. Like 10 times the H plus concentration goes up by like 1 pH. I mean, actually it would go down, but okay, so Ka and Kb, anion tends to decrease pH. Kb, Ka, okay. All right. What else from the slides?
I think for the most part, it's okay.
Mm-hmm.
There's some like conceptual ideas with like the binary acids and the oxyacids.
Mm-hmm. Oh, here's another version of the law of mass action over here.
Mm-hmm.
So yeah, binary acid is just like, so the thing that I showed you earlier with polyprotic acid. So binary acid is just like most normal acids, I guess. Like it just breaks apart into two things. Like HCl breaks apart into H plus and Cl minus. So that's like a binary acid. H3PO4 phosphoric acid is a triprotic acid. So, you know, it'll break apart, like first it'll turn into this H2PO4 minus, and then it loses another like hydrogen, and it'll just be HPO42 minus. Then it loses the last one, and it'll just be PO43 minus. So that's triprotic right there. And then here's a di. You said binary acid?
Yeah.
Okay. Yeah. This. Oh no. What am I talking about? That's salt. But yeah, the binary one would just be like, you know, two things. Mantissa. Okay. So yeah, here's some. Yeah, negative power minus the log of the mantissa to figure it out. Strong acids, we just use this. Weak acids, I don't think you've done anything with Henderson Hasselbalch yet, right?
No.
Okay. Oh yeah, and then here I talk about pKa, because when you take the P of something like pH or pKa or pKb, it's like it's an inverse like of Ka, because like, okay, for an acid to be strong, its Ka needs to be like high, but pKa is the negative log of that. So if it's a strong acid, its Ka will be high, but its pKa will be low. So I just wrote like pKa is inversely proportional to acidity. Yeah. Yeah, and then here I talk about like inorganic chem, which is something that, you know, you don't have to know, but it's entirely based on like Lewis acids and Lewis bases, and and what we call them in organic chemistry, like a Lewis acid we call electrophile because it likes electrons, and Lewis bases we call nucleophiles because they like the nucleus, and a nucleus is positively charged. So okay. What with the binary acids? Oh yeah, and are you able to tell like how like why this is like that?
Yeah, like the strength
Mm-hmm.
of like acids. Yeah.
Yeah. So like why is hydrofluoric acid weaker than hydrochloric acid?
Um, I think for that one it was electronegativity, and I think it was like because it is like more like one is more electronegative, it'll want to like take other um, electrons,
Mm-hmm.
and therefore it won't want the H plus
Uh.
ion as much.
Mm-hmm. So okay. If it's if it's electronegative, right? It will kind of like pull on it'll pull electron density from the hydrogen towards the like let's say fluorine, the thing that's electronegative, and since it's pulling electron density, it's going to make there be a dipole, like a positive partial positive charge on the H, and that makes it you know more likely to leave to gain some electron density from something else in the environment. Now, that's one of the reasons. Another reason is the size of the atoms. I don't know if you guys talked about size.
Um, like the radius and like the length,
Mm-hmm.
and like the longer the um, bond, the like weaker or the easier it is to like break apart.
Mm-hmm.
Mm-hmm.
Let's see. Yeah, because atomic radius gets larger as you go down and to the left. So fluorine is smaller than chlorine, which is smaller than bromine, which is smaller than iodine. I mean, yeah, iodine. Um, and yeah, the bigger that thing is, it makes it harder for it to make a strong bond because the stronger the bond is, the shorter it is. So short bonds will be strong bonds and hold on to the H. So yeah, it's a combination of its electronegativity and its size. Okay, binary acids across the row. Okay, oxyacids make sense.
Um, yeah, I think so. It's kind of the same with like electronegativity, and then like the amount of oxygen atoms present.
Mm-hmm.
I
Yeah, because oxygen is a very electronegative atom, and they pull electron density. So when that happens, the hydrogen just isn't getting satisfied, it seems, and it just wants to move on to something else and leave and break that bond. Um, okay. So you can tell like which acid would be a stronger acid based on what you see.
yeah, I think so. If
Okay.
I can have like a periodic table,
Yeah.
like yeah.
This seems to be like a good summary for it. Like
Mm-hmm.
binary acids, if you go down a group, because if you're going like across a row, things that change are mostly electronegativity, right? But if you go down a group, the electronegativity doesn't change too much, so that's when you compare bond length, which is basically like, you know, how big the like atom is. Like here, I drew this for you here. So maybe I should have drawn it like kind of bigger, but or maybe I'll draw this smaller. So like let's say we have hydrofluoric acid and hydroiodic acid. The iodine atom is much larger. So, you know, the bond, that's kind of bad drawing. But basically, like, from the center of these atoms is the bond. So this is the bond length for iodic acid, and this is for hydrofluoric acid. I mean, hydroiodic acid or whatever. And since this is much bigger, that bond length is longer. So the bond isn't that strong, so it's likely going to just lose the hydrogen. Whereas for fluorine, it's much smaller, so this bond length is shorter and therefore stronger. So yeah. So they just talk about bond lengths minus stronger bonds, and I just wanted to relate that to atomic radius.
Mm-hmm.
Okay. And for oxyacids, like the more oxygens you have, there's it actually talks about the stability of the conjugate base. So that's like another thing. The more stable the conjugate, like, you know, it could be the conjugate acid or the conjugate base, the more stable that is, the stronger the base or acid, respectively. So what that basically is saying that, because if you think about it, if the conjugate, like, for let's say we have an acid, right? It'll make a conjugate base. If the conjugate base isn't stable, it's going to be reactive, and it's going to react to not be that conjugate base anymore. So it's going to react to be the acid again, so the acid's not going to be that strong. But if it produces a very stable conjugate base, the conjugate base can just be itself. It doesn't have to go back and take a proton from the acid. So yeah, the stability of the conjugate part is like it is proportional to how strong like the base part is. So that's what the slide is saying: the stability of the conjugate base, happy, and less likely to revert back to acid. Exactly. The more electronegative the central atom, the more likely it'll ionize. Okay, electronegativity polarizes away from OH. Oh yeah, so yeah, for oxyacids, since there's a lot, when you have more oxygens here, they so let's say, you know, this, like, whatever, perchloric acid loses the H, you have basically like resonance here between all these oxygen atoms, which makes it very, very stable. So compare that to this, where if it loses the H, it's just going to be like, you know, like a negatively charged oxygen here and like whatever chloride there. But yeah, basically the more oxygen atoms there are, the stronger it is because of like resonance stabilization.
Mm-hmm.
So okay, so those are okay. Any other question from the slides?
Okay. We can probably like come back to it just to make sure I like remember.
Okay.
Yeah.
So let's look at that worksheet. Unless you got something new, like.
I mean, I have more things, but we can do that if we like run out of time or we have more time.
Okay. So let's see. Calculate the pH of each of the following strong acid solutions. Okay, so they're doing us a favor by telling us that they're strong acids. So, okay. So the first one, 8.5 times. Oh, they're just telling us the concentration of the acid, right?
Mm.
So how can we find the pH of that?
You would just do a rice box problem.
What's that?
You would just like do a rice box problem and then kind of split it up.
I'm not sure what a rice box problem is in particular, but we can figure it out just using like the log formula, like the pH formula. Because so we have the concentration of HBr, and since it's a strong acid, it's going to break apart like completely, dissociate completely. So this concentration is going to be true for the H plus concentration as well as the Br minus concentration. But since we just have to find the pH, we're only concerned with the H plus concentration, right? So that means H plus concentration is equal to 8.5 E negative, what is that? Negative 3. Right? Okay. So tell me how we can do this. And remember, you can use this over here.
So the negative exponent, so that would be 3.
So yeah, negative 3 minus
yeah, and then minus log of the mid, so which is just 8.5.
Good. So we basically get 3 minus log of 8.5.
Like 2.
What is it?
2.07. About.
Okay. Okay, yeah. So that's basically it for that problem. Let's see. B. 1.52 grams of HNO3 in 575 milliliters of solution. Okay. This involves another step. So walk me through this.
You would convert the grams and the liters to get molarity.
So what do we do first?
You take the grams and then you multiply it by the ratio of grams in a mole.
Yeah, gram formula mass, right? Or the molar mass. So okay, molar mass of HNO3 Let's see. Oxygen is what, 16? Let's see, 32, 48. Is that right? 48 plus 1, 49 plus 15, 59 plus 64. What is it?
63.02.
Okay. All right, so that's what I wrote over here. And then I want to divide it by the volume to get the molarity. So, I'll just do like this over 0.575 liters. And so yeah, tell me what you get for this.
Um, 0.0419.
Okay. So this is basically the same thing as the concentration of HNO3, right? Right, that makes sense?
Yeah.
Okay. And since it's a strong acid, it's going to break apart completely. So, H plus concentration will be this, and NO3 concentration will be this. So we just use, the H plus concentration of that. So, it's also going to be equal to the H plus concentration, also going to be equal to the NO3 minus concentration. And so we have to find pH. So the next step, pH, is negative log of H plus. So it'll be negative log of 0.0419. And so, okay, I guess, I will put this in scientific notation, so it's going to be easier numbers. I should have done that first. So I'll do that in blue. So this is the same thing as 4 point, I'll just say, or whatever, 4.19 E negative 2. Right? And so if that is the H plus concentration, what is this going to be if we use, this method?
It would be 2 minus log 4.19, and then that would be 1.38.
Yep. That's not too bad, right?
Yeah, that's good.
Okay. Now let's see. C, 5 ml of 0.25 molar H hydrochloric acid. Diluted to 50 ml. So okay. This is going to be, involve like another step. What do you think? How should we approach this?
Would you
So okay, let me ask you this. So let's look at the things that are changing and the things that are not changing. So volume changes, right?
Mm.
And Does molarity change?
No.
Are you sure? Because molarity is
Because since volume's changing, yes.
correct. But what won't change?
The moles.
Correct. So we have to find that. How can we find that?
You take the molarity,
Mm-hmm.
and then the 5 milliliters.
Mm-hmm. So okay, you can do this. So I wrote molarity 1, volume 1 is equal to molarity 2, volume 2.
Mm-hmm.
Right? And these are in moles. Okay. So molarity 1 is 0.25 times 5 ml. So basically that's like 0.005. So I'll just write 5e negative 3 liters. I guess I should have done that. Okay, so 0.25 molar, okay, is equal to, so molarity 2 is what we need to find, but volume 2, so it says it's diluted to 50 ml, so volume 2 is just, 50 e negative 3 liters.
Mm-hmm.
And now we could just divide both sides by 50 e minus 3 liters, right?
Yeah.
Sorry, my L's look like C's or something. Okay, so we basically will then have, so divide both sides by 50 e negative 3 liters. And we basically, so 5 goes into this once, goes into this 10 times. And this is basically 1/4. Goes into that once, goes into this 40 times. So I get, well, alright, forget the 40 thing. So I would get, let's see, 1/4e negative 3 divided by 10e negative 3. And this just turns into 1/4 goes in divided by 10 is 1/40. Then e negative 3 minus negative 3 is 3 minus 3. What do you get in your calculator?
I got 0.025.
Yeah. Okay. Good. I got that too. So, yeah, 1/40 is 0.0225. Okay. Cool. So, oh yeah, that's the okay. So that's the new molarity, and okay, and it's also going to be the H plus concentration, right?
Mm-hmm.
And so, okay, might as well turn this into scientific notation. So 2.5 e negative 2, right?
Mm-hmm.
And so the pH is going to be what?
It would be 2 minus log 2.5.
Mm-hmm.
And then that would be 1.60.
All right. Yep. Good job. All right. So yeah, and like to do a like sanity check just to make sure that our numbers match with the concept. Like yeah, they're strong acids, so the pH is gonna be low. So like we have like 2.07 here, we have 1.38 here, we have 1.6 here, and that's after diluting it. So okay, everything makes sense conceptually. Any questions for those?
No. Okay.
Okay. Now let's see the next one. Whoops. All right. 0.085 molar solution of this. So let me ask you this: do you think this is going to be a strong or weak acid over here?
Weak.
Yeah. Yeah. This is a benzene ring with another carbon attached to it, which is attached to a carboxylic acid.
Mm-hmm.
So, okay, so it has a pH of this. So if we have this and the pH, right, we can basically figure out. So, okay. Wait, they're asking us to calculate the Ka? Is that what that says?
Mm-hmm.
Okay, Ka, right? Okay. So, let me move over to the left of it. Okay, so we have, number 2. Okay, so the Ka value, okay, so Ka is basically going to be like whatever, the like acid concentration on the bottom. And I don't want to write the entire thing out. I'm just going to write HA. Like instead of the writing all this out, I'm just going to use that as HA.
Mm-hmm.
And it's going to turn into like whatever, like A minus, the conjugate base. Yeah, one sec. Let me take a look at something. Okay, whatever. So, all right. So this is going to be, okay, whatever. So all right. So, okay, we need to find the Ka value. So we know what the Ha value is. We just need to know the A minus concentration. But actually, it will turn into this, like not just A minus, but H plus. And so they give us the pH so we can figure out the H plus concentration, and they give us the concentration of the HA, and then we can solve for Ka. So okay, H plus concentration is going to be what if the pH is 2.68?
10 to the negative 2.68.
Mm-hmm.
Should be 0.0021.
All right. Okay, all right. Okay. So wait, what is this rice box stuff?
It's like setting up like the reaction at the top, and then you have the concentration of 1.
Oh wait, initial change and equilibrium? Is that what the ice part stands for?
Yeah, I think so. I don't remember what the acronym is, but.
Mm-hmm. Okay, and you never did anything like this, so alright, forget that. Where did I talk about this? I wonder if I could use KW. Probably not. Okay, whatever. So, okay. We have the H plus concentration. We need to find the Ka, which should be this. So that would be the 0.085. Conjugate base that's left. I wonder if it's just like the total minus this.
I think usually it's the same as H plus, I think, when we set it up.
Mm-hmm.
Because usually we can simplify it to just like x squared. Because they'd both be like the same.
Yeah, okay. Yeah, I guess that makes sense. Oh yeah, no, that makes perfect sense. Yeah, it shouldn't be equal to 0.085 because not all of it has associated. So okay, good job. Okay, so we can do this. Ka is equal to let's see, 2.1 e negative 3. I'll square that over 0.0. Well, I guess I'll do it in scientific notation. 8.5 e negative 2. Okay. So, what do you get if you put that into your calculator right there?
It's like 5.2 to the, or E, and then negative 5.
Negative what?
5.
5?
Mm.
Okay, that's the Ka. That's all we need to find. But if I asked you what the pKa is, would you be able to tell me what that would be?
Just plug the Ka into the like pH.
Mm-hmm. Yeah, you do it exactly how you would do pH.
Mm.
Right? If this was pH, or rather H plus whatever, the P of it, you do it the same way. So basically it'll be, this, negative this, minus log of that, right?
Mm.
Negative 5 minus log of 5.2. And that'll basically be at 5 minus log of, log of 2 is 0.3, log of 3 is 0.5, I think. Log of 5, what was it? Oh, okay. Yeah. Log of 5 is 0.7. Log of 7 is... Oh, that kind of works out. 0.9. So it'll be roughly 5 minus log of 5, or 5.2, but it's close to like 0.7. So, it should be something like 3 something.
Yeah, I got 4.28.
4 point what?
28.
2.8. Oh, yeah. So, yeah, that makes sense. Because log of 5 is 0.7, and 5 minus 0.7 is 4.3, but the actual thing is 5.2, so it should be a little higher. And if you're subtracting it by something that's larger, so it should be a little less than that. So, okay, good. So that's just, for P anything, that's, you do the same thing. All right, lactic acid has 1 acidic hydrogen. A 0.1 molar solution of lactic acid has a pH of 2.44. Calculate Ka. Okay. It seems like we would just do this the same way.
Mm-hmm.
Right? So let's see. 3. So... okay. 10 to the negative 2.44 is the H plus concentration. Ka is equal to whatever that is. What do you get for that? 10 to the negative 2.44?
3.6 E negative 3.
Okay. So I'll do 3.6 E negative 3 squared over 0.1 and yeah, that'll be your answer, whatever that is. 3.6 squared, it's going to be greater than 9, less than 16. In the middle would be 12.5, so it'll be a little bit more than 12.5, maybe like 13.
Yeah, I think it's 1.29.
Cool. Okay. Oh wait, you said 1.29?
Yeah, and that's
for the entire Ka or for part of it?
Yeah, for the entire thing.
Oh, okay. Got it. Oh, yeah.
So that,
That makes sense. Because you're dividing it by this, which means you're multiplying it by 10. All right. Okay. That wasn't too bad. Let's see. All right. 0.1 of chloroacetic acid is 11% ionized. Okay. Using this information, calculate Ka for chloroacetic acetic acid. Okay. So I'll do this above. So 4. So this kind of helps us out in the sense that it shows how much is ionized, right? So, okay, Ka is equal to, denominator would just be 0.1, molar, and 11% of that, right? So 1 over 10 is 0.1, right? And we need to find 11% of it. So we can multiply it by 11 over 100. Or, you know what? I could have just... Well, whatever. I'll stick to that. 11 over, 1,000, right? So 11e negative 3, right? Like 11e negative 3, that's 11% of 0.1.
Yeah.
Okay. Chloroacetic acid. Okay, yeah. So then it'll break apart into the two things, so I can square that. So 11e negative 3 squared. 11 squared is 121. Negative 3 times 2, negative 6. Divided by 10. Or multiplied by... Wait. 0.1 is 1 over 10. I'm multiplying it by 10 to get 121e negative 5, which is just 1.21e negative 3. Is that what you end up getting?
Yeah.
Okay. Particular sample of vinegar has a pH of... Yeah, acetic acid is what's in vinegar, by the way. So pH of 2.9. If acetic acid is the only acid that vinegar contains, and it has a Ka of that, calculate the concentration of the acetic acid in the vinegar. So, whoops. Oh, man, why did I do that? Okay. I'm just going to move that over here for more room. So, all right, number 5, vinegar, pH of 2.9. Okay, so when you see pH, what are you going to do with that?
Convert that to like the H plus. Concentration.
Yep. How do we do that?
10 to the negative 2.9.
Yep.
And that is 1.3 e negative 3.
All right. And that's, the H plus concentration. Good. And then they tell us that, they give us the Ka, which is 1.8 e negative 5. And we just need to calculate the concentration of acetic acid, right?
Mm-hmm.
So we could just do 1.3 E negative 3 over here squared over concentration of HA. And I'll just algebraically manipulate this to get HA concentration is equal to 1.3 E negative 3 squared over 1.8 E negative 5. So yeah, what do you get for this?
0.094.
0.094?
Mm-hmm.
All right. Yeah, so that's 9.4 E negative 2. And, like, yeah, you could do you know what I mean when I say a sanity check?
Yeah, just to like make sure it like checks out with like the logic.
Yeah, like, so, it's a weak acid, so this HA concentration should be larger than, the H plus concentration and stuff like that, right?
Mm.
And it is. So, good job. Let's see. The next one, calculate the molar concentration of hydroxide ions in 0.075 solution of ethyl amine. And they give us the Kb here. Calculate the pH of this. Okay, so this is going to be a little different, but not too different. So okay, Kb, right, is going to be, they give it to us. Molar concentration, okay, so Kb okay. Ethylamine. Should I use H? Well, okay, well, I mean, break up into OH minus ethylamine. Oh, and by the way, you see the structure or the molecular formula for ethylamine?
Yeah.
So do you notice any oxygens there or any, I mean, it doesn't really have it doesn't really donate a proton either. So this is like a good example of a Lewis base.
Mm-hmm.
And okay, so all right, so Kb. So on the bottom, I mean, like I know it's gonna be ethylamine. But I shouldn't write Ha. Yeah, whatever. I'll just write ethylamine. Whatever. And on the top, it's gonna be like OH minus, and then times whatever conjugate acid, I suppose. Conjugate acid. Jesus, I guess that's like H. Hey. Well, so okay, this like is gonna work. I just don't remember, like, don't know how to put this in terms of like HA or not.
Mm-hmm.
So I'll just leave it like that. Maybe I'll do like conjugate acid here. whoops, like conjugate acid, okay. And here I'll just put, the base, which is the ethylamine. Okay, so okay, Kb is 6.4 E negative 4. That's equal to whatever. I guess I could just do x squared over 0.075 and solving for x will give us the OH minus concentration. So yeah, what do you get when you multiply this by that? What do you get?
I think it's 4.8 to the negative, and then E negative 5.
That's x squared? Or just x?
Oh, no, that's just that. And then the square root of that would be, that would be 6.9
What was that?
negative 3.
Oh, okay. All right, so that is the OH minus concentration. And what were they asking for? All right. Okay, so we have that. And then we just do pH. So we could do a couple of things to get pH here.
Mm-hmm.
We could... So, all right, what I'm going to do is I'm going to find the pOH, and then I'll subtract it from 14.
Yeah.
To find the pH. So okay. pOH would be?
It would be 3 minus log 6.9, which would come out to 2.16.
All right, good. And then 14 minus 2.16, that's going to be 11.84. Yep. And it's a base, so the pH is going to be, closer to 14, right?
Mm-hmm.
All right. So that was just, the same thing, but we just had to do, for OH concentration stuff. 7 seems to be exactly the same. Let's see. Hyperbromite ion. Let's see. Ephedrine, a central nervous system stimulant, is used in nasal sprays as a decongestant. This compound is a weak organic base. Okay. So they show us the reaction that it does with water. And this solution of ephedrine has a pH of 11.33. What are the equilibrium concentrations of this, and that? And then calculate the Kb for ephedrine. Okay. So So, okay, how should we attack this problem?
So convert the P. Well, should you convert it to POH actually first, or just pH?
Well, I suppose you could do that. That would just be 14 minus 11.33. Okay, let's take a closer look at what's happening here. So basically, this is the base over here, weak organic base, and then this is the conjugate acid, right? And and then this H2O over here is acting as an acid here, so this over here is the conjugate base for the H2O. So I'll mark it like this. So this is the base, and it turns into conjugate acid. Probably should have made my thing skinnier. Here, this acts as an acid. So here is its conjugate base. Does that make sense?
Yeah.
So they're asking for the equilibrium concentrations of the base, which is reactant side, and will be the denominator, right? The conjugate acid and the conjugate base. So okay. So equilibrium concentrations of these. All right, I'll write it on the left. So, okay, 8. So, okay, so I'll just start with equilibrium is equal to, so on the bottom, it'll be, the C10, whatever, C10H15ON as a reactant, right? And on the top, it'll be, the C10H15ONH plus times OH minus concentration. Oh, yeah, here it is. I'll talk to you later. Okay, so okay. So we have the concentration of this over here.
Yeah.
It's 0.035, and it has a pH of 11.33. So okay, yeah. You know what? We could turn that into POH to get a better idea of the OH minus concentration. Okay. So all right. So we'll do that. So if the pH is 11.33, POH is going to be 3.6. I don't know, like 7, I guess. Something like. Wait, what am I doing? POH, 14 minus that. That should be the POH, right?
2.67.
Oh, okay. All right, so okay, that's the POH, and okay, and then we're gonna use the pH to find the H plus Wait, what am I? Sorry, we're going to use this POH to find the OH minus concentration.
Mm-hmm.
So that is going to be 10 to the negative 2.67.
And then we get 2.1 E negative 3.
Okay, that's the OH minus concentration. So we got that. And okay, I guess it would be the same amount as this.
Mm-hmm.
Okay, so I'll just do it. Oh wait, for the equilibrium, we don't even have to calculate the equilibrium K, the equilibrium constant. They're just asking for the concentrations of these. So OH concentration is that. The ephedrine concentration is 0.035. And I believe the conjugate acid should be the same thing as OH minus, right?
Yeah.
Okay, so that's A for that question. And then B, we just have to calculate the KB.
Mm-hmm.
So KB is equal to okay, so like the bottom will be 0.035 and the top I guess would just be 2.1 E negative 3 squared. Tell me what you get for this one.
1.3 E negative 4.
Okay. And just for fun, tell me what the PKB is for that.
B. It's 3.89.
Okay. All right, this makes sense now?
Mm-hmm.
All right, now we have hydrofluoric acid. So this is what happens when it's in water. It gives us the Ka value. Write the equilibrium constant expression for the dissociation of HF in water. So we'll do that. So 9A. We will have okay. Okay, I mean the Ka and the equilibrium constant should be the same, right? Oh, we just have to write the expression. So okay. I mean okay, so KEQ is equal to hydrofluoric acid on the bottom and H3O plus on the top times fluoride ion concentration on the top. So that should just be the expression for that. And let's see, B, calculate the molar concentration of hydronium in a 0.4 molar HF concentration solution. So now we just have to plug in 0.4 for HF concentration. And we could set it equal to Ka. And then... Oh yeah, and then these would have the same concentration. So we just have to solve for that. It'll be like x squared and then square root of that. So, okay. Ka is equal to, the same thing. So we have x squared over 0.4 is equal to Ka, which is 7.2 E negative 4. So 0.4 is 2 over 5. I can multiply both sides by 2 over 5. Or I'll just let you do it, I guess. In your calculator.
So I get x equals 0.017.
Okay, so it should be 1.7 E negative 2. Oh, it doesn't even show this one. What do you get for this? I'm just curious.
1.77.
Okay. I mean, that should be it. It's, for some reason, seems like it's a lower pH than I imagined. But whatever. Oh wait, you know what? I kind of didn't do the ice tables for these. Ice tables for these. All right. Because okay. Because all right, for the ice table, it's like the equilibrium thing. So all right, let me just do like a sanity check here in purple. So if we have HF turning into H plus F minus, initial HF was 0.4. Of course, 0, 0. For these, the change would be minus x here, plus x, and the equilibrium then would be 0.4 minus x, and then x, and then You know what? Okay, I think it should be fine. Oh yeah, it should be fine because that's if you like dissolve it in a solution or something like that. I mean, this would be x. The only thing that would change is the denominator being 0.4 minus x, but x is, I mean, that's pretty small, isn't it? X is that 0.4 is that 0.4, wait, 0.4, and then this is 0.017. Whatever, that's pretty small. I don't think it'll change too much. Okay. 10, aniline is a weak base. Reacts with water according to the reaction represented above. Write the equilibrium. Constant expression Kb for the reaction represented above. Alright, I mean, you know how to do that, right? It just concentration of this times concentration of that over concentration of that, right?
Mm-hmm.
Alright. And B, a sample of aniline is dissolved in water to produce this volume of this, like, concentration. So right away, like, before even reading the rest of it, I know that this and this enables me to find what? I mean, we probably don't even have to find it out, but if you're ever given concentration and volume, you can find the moles, right?
Yeah.
Okay. Now the pH of the solution is this. Calculate the equilibrium expression constant Kb for this reaction. Okay. Dissolved in water to produce that much of solution. All right. 10. I will write like over here. So we have a sample is dissolved in water to produce. Okay. I'm trying to think. All right, whatever. I'm just gonna go for it. Kb is equal to, like, whatever. The aniline to produce the conjugate acid and the OH minus. So aniline is dissolved in water to produce 25 ml of 0.1 molar solution. The pH of the solution is 8.82. Calculate the equilibrium constant. Okay, let's see. pH is 8.82. So 10 to the negative 8.82. What do you get for that?
2.0, and that's E -9.
Yeah, I should have had you just do POH actually. and then use that to get the OH minus concentration. So POH would be 14 minus 8.82. 5.18, I think.
Yeah.
Alright, what's 10 to the negative 5.18?
That would be 6.6 E negative 6.
Alright, that's the OH minus concentration. So we have the OH minus concentration, we have the aniline concentration, and I'm assuming that this is going to be the same concentration as the OH minus concentration.
Mm.
I just don't know what to do with that 25 ml thing, but whatever. And then I guess we just solve for Kb, I suppose. So, okay, so what do you get if you then have, Kb is equal to 6.6 E negative 6 squared over 0.1.
4.4 E negative 10.
All right. I just looked up aniline's Kb, and that's pretty much it. I mean, the thing that I see is 3.8 times 10 to the negative 10, so we're pretty much right. Because that, depends on how much is used and stuff. So, yep, that's Kb for aniline. Does that make sense?
Yeah.
Okay. We still have some time. Do you want to send me any additional work? Unless you have questions on any of this stuff.
No, I can send you the.
Okay.
Okay, I think it should have sent.
Got it. Okay, so use the following information in the table to answer part A at 1, I guess. All right. Which of the two acids is stronger? Okay. So, which of the two acids are stronger?
Okay, I might have to look at it.
So, what does Ka represent?
It's the ratio of reactants to products.
And the stronger an acid is, the more it'll produce products, right? H plus products.
Yeah.
So it'll be Ka basically so Ka is proportional to acid strength.
Mm-hmm.
So okay, which one has the larger Ka?
Um, so H OCl.
Yep. So yeah, so for what is this? 1A Roman numeral 1, it's going to be HOCl because its Ka is greater than that of, the other one. Okay, Roman numeral 2, Lewis electron dot diagram for the acid that you identified in that. So you remember these, right?
Yeah.
So it'll look like this. Yeah, it'll look just like that. All right. Hypoiodous acid has the formula HOI. Predict whether HOI is a stronger acid or a weaker acid than the acid that you identified. All right. What do you think?
I lower than like HCl in the periodic table.
Which means what?
It would be stronger.
So, okay. Why do you think it'll be stronger?
Cause wait, is it in the same group? Okay, then because the atomic radius will be bigger, and then the bond will be weaker, and so it can break up easier.
Yep. So yeah, I would write like iodine is larger, in terms of atomic radius. So its bond to hydrogen is longer and therefore weaker. Make sense? All right, then B. Write the equation for the reaction that occurs between hypochlorous acid and water. So, like, it's like hypochlorous in terms of weakest to strongest. Hypochlorous, chloric, and then perchloric. So, you have like the hyper thing, and us versus ick. Us is like weaker than ick. Okay, so alright, so we're just basically gonna draw that right there. So HOCl plus H2O yields H3O plus I guess OCl minus.
So like Cl minus.
Yeah, I think it's. Oh wait, you know what? Okay. Yeah, I think it'll be like that.
Okay.
Yeah, and since they're not asking us to draw like Lewis dot diagrams, it doesn't really matter where we put the negative. But I think technically it would be on the O. But yeah, same thing with, see how OH minus, the minus is at the end, but the minus sign is really on the oxygen. So, but okay, so let's look at, all right, then C. 1.2 molar NaOCl solution. So that's just going to break up into Na plus and OCl minus. Is prepared by dissolving solid NaOCl in distilled water at 298 Kelvin. The hydrolysis reaction of the OCl minus plus the H2O produces Well, it seems like it produces hypochlorous acid. And it also produces OH minus. Interesting. Write the equilibrium constant expression for the hydrolysis reaction that occurs between OCl minus and H2O. So we just have to draw, the K thing for C. For Roman. So K, whatever equilibrium, is going to be HOCl concentration times OH minus concentration over OCl minus concentration. That makes sense?
Yeah.
All right, then calculate the value of the equilibrium constant at 298 Kelvin for the hydrolysis reaction. So, this thing will be 1.2 molar, and wait, oh wait, give us a Ka over there. So I think we'd set it equal to that. All right, we could do that. Oh, okay, so we can do this, set it equal to that, and plug this in for, OCl minus, and then do x squared over there. Wait a sec. Equilibrium constant. So, all right, first I could do this to find like this over here, like the numerator value. Then I could plug it back in for there and then use the 1.2 molar for this. And I'll get a new value, which will be the equilibrium value. So, okay, that's what I'll do. So, okay, Roman numeral 2. So, Ka is equal to 2.9 e negative 8. And that is equal to x squared over what are we doing here? If I use Ka, I don't know what to put for the HO. Okay, wait, this is the opposite of this. So, gotta change that. So this would just be H plus times. Okay, and it's a strong acid, I believe. A minus HA over here. Equilibrium constant for this. Ka is that. Equilibrium constant's this. Ka is this. Ka at 298 Kelvin. I don't have any other information here. Like, I know this over here is 1.2. Would that be there? Have any ideas?
Not really. I don't think I've ever had one where it was missing like the Ka and like that top one, but I mean, I think this type of problem, you can probably find a solution online.
All right, see if you can find the solution online. I'm going to look in your PowerPoint to see if I find any clues here.
Okay, yeah. I will. I can email you the link.
Okay. Oh, it's straight out of an AP Chem test. Okay. All right. All right. Damn. Yeah. I was looking at that in like this notebook over here. Wait, where'd it go?
Mhm.
Like over here. Ka times Kb is equal to Kw, which is this. So that means Kw over Ka is equal to Kb.
Yeah.
So, and we're going to use Kw because it's in water. That's what you use for water. All right, that makes a lot more sense. Okay, so let's see. So Roman numeral 2 is Kb. Okay, so let's see. Okay, so Kb is equal to Kw over Ka, which is Kw is always 1, to the negative 14, and they give us 2.9 e negative 8. And I guess, once you do the math, it's 3.4 e negative 7. Oh, yeah, let me move that. 3.4 e negative 7. Okay, so okay, I guess this equilibrium stuff isn't really like equilibrium. It's Kb. It's a different type of equilibrium. I should have remembered that for like acids and bases. So okay. Equilibrium constant for the hydrolysis reaction would be this. Oh, I forgot about this part, which is OCl minus. Okay, and then part 3, calculate the value of the OH minus in the 1.2 molar solution thing. So now we just have to find this over here. Okay, and then they use an ice. Okay, the ice thing. So initial value. All right, I'm gonna do the ice thing. So I'll do it in green. So 3. So we have ICE, and we have OCl minus. We have HOCl, and we have OH minus. Initial value was 1.2 for this, 0 for that, 0 for that. Change minus x here, plus x, and then the equilibrium value 1.2 minus x, then x. So then for and then we take what we got for Kb here, plug it in here, put an x here, an x here, and then for this, put 1.2 minus x.
Mm.
And I think, like, since it's small, you basically make it negligible. So, okay. So, basically, alright, so negligible. So, this is just going to be, again, KB. Alright, no, I won't rewrite KB, but I'll just write 3.4 E negative 7 is equal to, well, alright, I'll write it and then I'll manipulate it algebraically. So this is equal to HOCl concentration times OH minus concentration over OCl minus concentration. And we have to find OH minus. Oh, sorry. We have to find OH minus, so I'm going to do, whoops. So I'm going to do OCl minus concentration times Kb divided by HOCl concentration is equal to OH minus concentration. So I just algebraically manipulated that. And now I just plug in numbers. So yeah, plug in. And I get 1.2 1.2 molar here. Kb was 3.4 E negative 7 over, that's just going to be x. And this is going to be x. I should have left the x's on this side.
You just square root, right?
Mm-hmm. So 1.2 times 3.4.
I think it would be 6.4 times or E negative 4.
Negative 4, you said?
Yeah.
Oh, yeah. Yeah, that's it. So, okay. So, it seems like for the most part, we didn't really have to use, like, the equilibrium value of what changed in the reactants. But, oh, and then I guess the main important thing here that I forgot at first, I'll put it in, like, red, is that equilibrium constants for acids/bases are not KEQ, but Ka and Kb, respectively. So I wrote that there. So yeah, that's what I was doing wrong over here by making it KEQ and stuff.
It would be KW instead.
It would be like if it's a base, it'll be Kb,
Mm-hmm.
and if it's an acid, it'll be Ka.
Mm-hmm.
And if it's like an acid that you drop in water, like for hydrolysis or something like that, right? That's when you would start to use like KW. But actually, you know what? This thing over here, so I'll just add that as well. um, Ka is equal to Kw over Kb, and likewise Kb is equal to Kw over Ka, and this is all because Ka times Kb is equal to Kw, which is equal to 1e negative 14. Oh, that's bad looking 14. Right there. So, yeah, so I basically wrote equilibrium constants for acids/bases are not Keq, but Ka and Kb respectively. And Ka is equal to Kw over Kb. And Kb is equal to Kw over Ka. And that comes from this. When you the product of Ka and Kb is Kw, which is 1e negative 14. So that Kw value is always constant. The Ka and the Kb will change, but you'll be able to figure out one from another based on the Kw that doesn't change. Okay. So everything makes sense here now?
Yeah, I think so.
Okay. So when's your next test?
Tomorrow.
Tomorrow?
Mm-hmm.
Okay, so what... So from these questions that we just did, what is the most difficult?
I think probably for this one, it would probably be like more of the conceptual ones, like the conceptual questions. I can I think I have the last test. I can send you the format of it.
Mm-hmm.
How it's formatted. Because there's usually some explain questions.
Oh, like in the PowerPoints, there are some questions that are let's see. Are you talking about conceptual problems? In the PowerPoint, I see things like, how can you identify if you have a polyprotic, or rather, something like, explain when comparing acids down the same group, find a pattern and explain why the acids are ordered from weakest to strongest. Is that kind of a conceptual problem or question that they would ask you, or?
Yeah, kind of, but he always makes it a little more difficult than what's on the slides.
Any examples?
Yeah, I can send it the last units to you.
Mm-hmm.
I mean, it's the last unit, so it's kind of different, obviously, but
Mm-hmm.
Yeah, I should get that.
What's that?
It should have sent, I think.
Oh, let's see. Okay. All right. So let's see. Strongest IMFs. So wait, what are these the types of? So what is this that you sent me?
That's the last test. So those are like kind of like the test questions. Like
Uh-huh.
it would be similar.
Are these the conceptual ones that you're talking about?
That's just the whole test. Like there's like more conceptual like ones where it's like um
Let me ask you for 8, it seems, A,
hmm,
when it says elaborate your answer to the best of your knowledge, is that the short answer question?
yeah, I'll look at my yeah, like I think for like 2, 7, and like 8.
Oh, I didn't even see the other ones. All right, sorry. Now I see it. I didn't scroll down. Okay. Let's see. Cohesion. So wait, you said something about 2 and
2, 7, and like 8. Those are the kind of ones where
oh, okay. 2. Let's see. Sea level water has a boiling point of 100 degrees Celsius. Decane is non-polar, has a boiling point of 174. I see these types of questions. Okay, this gives me a much better idea. And these are like short answer ones, right?
yeah.
Um, I mean, okay. What did you like say?
I said at sea level, C10 H22 boils at 174 degrees Celsius. It's because even though the molecule is nonpolar, it only has LDF intermolecular forces. The forces are still stronger than the water's IMF. Furthermore, the forces are stronger and a greater temp is needed to break apart the attractive forces to reach boiling point.
Um, was the answer it's heavier?
Um, Let me see if we marked that one out. I think he might have. He definitely marked one of the explanations wrong.
Mm-hmm.
Yeah, he said elaborate on like size and like how that affects IMF.
Yeah, because you know, water, like the strongest intermolecular force is what? What type of bond?
The hydrogen.
Yeah. So that's why water has, a relatively high boiling point. Decane can't do any hydrogen bonds. And it's non-polar, and water's polar, and like dissolves like. So it's not even really dissolved well in water. So so it's not making like any stronger bonds with the water. So it's not going to be intermolecular forces for this one. It's just that it's a really big molecule. And if you're boiling something, you're basically turning it into like a gas where it can, go go like against gravity. And if it's a heavy molecule, it's going to have a harder time to, you know, for liftoff. So so yeah, for that one, you would answer it like, um, so it says use your knowledge of chemistry to explain why, and then elaborate with as many chemistry concepts as possible. So you want to use as many like words, like chemistry words. So like I would say something um, like something like, uh, so I would say something like decane is not completely dissolved in water because it's nonpolar and water is polar. Decane also doesn't make any hydrogen bonds. Um, So it's not a matter of intermolecular forces. However, decane is much, much more heavier. And that's why it requires more heat energy to get it to turn into the vapor phase. Because if you think about it, like, so water weighs like 18 grams per mole, right? And decane, so one carbon is 12 grams per mole. And this has 10 of them. So that's 120 grams per mole plus the 22. So that's 142 grams per mole, right? So it's a lot heavier. So that's how you would answer that one. Does that make sense though?
Yeah.
Like when you're thinking about like boiling points and stuff like that, it's right to think about intramolecular forces. It's right to think about like if a polar substance is dissolved in a polar solvent, like dissolves like. But also think about how heavy it is. Then I see. So you said 2, and then what was the other thing that you said?
I think 7 and 8 were the other, like conceptual ones. I think.
Okay, 7. That's the one that has the unknowns and the ones with the strongest intermolecular forces to the weakest, right? Okay, so that heat of vaporization, that enthalpy for vaporization, that's how much energy is needed per mole for that like compound to boil, right? To get into the vapor phase. So if it requires more energy, it's going to have stronger intermolecular forces, right? I mean, of course, unless it's, decane or something where it's just heavier. But yeah, so that one should be like the one that's 39.6 kilojoules, followed by 36.4, followed by 26.7. Is this right? Followed by 23.3.
Yeah. I think for my answer, I just put A to X.
What's that? A to what?
A to X.
Oh yeah. So okay. So like A2X followed by C3X2. Okay, good. And then B seems to be exactly the same question.
Yeah, sometimes it's.
And then you said 8.
Yeah.
Okay, so we have carbon disulfide and carbon tetrachloride. And we'll finish in like a few minutes. Let's see. Draw both structures with the correct 3D shape. So you're gonna draw like a Lewis structure, and then you're going to try to draw it with the bond like geometry. Do you remember that stuff?
Yeah.
Like okay, so okay, what does the carbon disulfide look like?
It was just
Yeah, and like what does like tell me about the bonds and stuff.
it was Flyro, although both molecules are nonpolar, CCl4 has a higher boiling point because it has stronger LDFs present between the molecules than
Stronger what?
Stronger London dispersion forces present between the molecules than CS2, and this is caused by CCl4's greater amount of electrons which increase the magnitude of the blended dispersion forces?
I mean, I think this is going to be the same as the other answer, where it's just heavier. Is that to tell you the answer for that one?
He didn't mark me wrong on that one. So.
Okay. Yeah. So, yeah. So just tell me what does the carbon disulfide look like if you drew it?
So it's two. There's S and then two on, and then C and two X.
Mm-hmm.
And, two pairs on the acid.
Yep. Good. So like it basically is a lot of times you'll see something that would normally be an oxygen, but a sulfur instead, because sulfur is like right underneath oxygen, like a group in the same group. So carbon disulfide is basically just carbon dioxide, but with sulfurs instead. And the double bonds make it so it's linear. If it was a single bond, it can go like in a lot of different directions. So that helps that. And okay, so now I have a better idea of conceptual ones. So your test is tomorrow. So yeah, let me know how you do and send me like more of these types of questions for like your test tomorrow. And yeah, so yeah, good luck tomorrow.
Thank you.
All right, and that's it. No more questions. What's up? Okay. All right. Good luck. Okay. All right. Take care. Bye.